Hello guys, today we are going to talk about infinite sequences and series. So first of all, we will see what is sequence. Sequence is actually a list of things, usually numbers, that are in order, right? Or a sequence can be thought of as a list of numbers written in a definite order. We can see here this is actually a sequence in order, right? And it's an infinite sequence because we cannot define its particular limit, right? So we have a1, a2, a3 up to an, right? And still it is going on and on. So we can say that a1 is the first term, a2 is the second term, a3 is the third term, a4 is the fourth term, and then an is the nth term in this infinite sequence. So when we talk about the order, the sequence is in order, we say that we are free to define that particular order. That order could be a forward order, a backward order, or up and down order, right? So this order is actually a forward order. We can see that our a1, a2, a3, a4, right? If this order was in this way, a4, a3, a2, a1, then we can say it's a backward order. So now we're moving to the notation of our sequence. We can see this sequence can be written as a1, comma a2, comma a3, and up to so on, right? So there are actually three things involved in this particular notation of the sequence. First is we list down all the elements, right, which are the a1, a2, a3. Then we separate them with the help of comma. And thirdly, we enclose them with the curly brackets, which are also called braces. And you can see over here, we can also write down as a sub n into the parentheses or brackets, a curly bracket, right? Or an, where n is equal to 1 and goes to the infinity, right? So this is actually the notation of a sequence, an infinite sequence, right? So some sequences can be defined by giving a formula for the nth term. So we have an example over here, and in that example we will be having the three things. First one would be the preceding notation, right? Second one would be the defining formula, and the third one would be terms of the sequence. So you can see over here in the A part, we have this particular thing is as preceding notation, right? And when we move over here, this is our defining formula. And thirdly, this thing is the terms of the sequence. So it is very simple. When we just plug in the values over here, when we plug in 1 instead of n, or we plug in 1 in the n, we will find 1 by 2 as an answer of this particular formula, right? Or this particular equation. So moving ahead, what's going on? All right, moving ahead, we have another example, that is part B. And in the part B, we can see three things over here, right? The first one is preceding notation, second one is defining formula, and the third one is our terms of the sequence, right? So we simply just put the values, plug in the values. We can just replace our n with 1, then with 2, with 3, with 4, and we will be finding these values over here, right? Minus 2 by 3, comma 3 by 9, minus 4 by 27. So these would be the values we get. All right, then we have another C example, and same way, but there's a slight change over here, right? So what happens over here, we have this preceding notation in which it says are n minus 3 under root and then n is equal to 3. It means that n would be starting from 3, right, and goes to infinity. So in the defining formula it says, that under root n minus 3 and then our n would be equal to or greater than 3. It would not be less than 3. It would not be 2. It would not be 1, 0 or the negative numbers, right? So what do? We just straight away plug in our 3 instead of n over here and we find the answer 0. Then we plug in 4. We find the answer like 1, and then under root 2, under root 3 and up to under root n minus 3 and up to so on, right? So this is how we just plug in the values over here and we're simply finding the sequences over here, right? Similar manner we have the D example over here and in this example it says that n is equal to 0, right? And we have to start from 0. Our value of n must be 0, and then we will starting with the increment of 1, then 1, then 1, then 1. It will be n is equal to 0, n is equal to 1, n is equal to 2, 3, 4, and then we'll have these answers, and we can just determine our sequence like 1 under root 3 by 2, 1 by 2, 0, and up to so on, right? So these are actually examples of our sequences. All right, now we have another thing that is called series. Now what is series? Series, actually it sounds like the list of numbers, but it's actually when we add them together, right? That is called series. When we have sequence of values, follow a particular rule, and we add them all, it makes series. So we can see that this is actually an infinite, this is a series of infinite decimal. You can see over here, we can see pi is equal to 3.14, and then there is a continuous, these are the continuous numbers over here, as it's going to forever, right? So the convention behind our decimal notation is that any number can be written as an infinite sum. Here it means that our pi is equal to 3 plus 1 by 10 plus 4 by 10 square plus 1 by 10 cube plus 5 by 10 raised to power 4. So it goes on and on and on, right? And when it comes to 3 dots, that indicates the sum continues forever, and more terms we add, closer we get to the actual value of pi. So in order to get the actual value, we have to just continue adding more terms, right? In general, we try to add the terms of an infinite sequence, right? A sub n, and then n is equal to 1 and it goes to infinity, right? We get an expression of the form a1 plus a2 plus a3, right? And then a4 and up to an, then up to so on, right? This is called infinite series, right? And when we talk about the notation of this series, we have actually sigma involved in this particular notation, right? So we have sigma over here. That means after sigma we have something which is a sub n. So it means sum whatever is after sigma, right? Sum whatever is after sigma, it is an. And what values of n we have to sum? Then we see the values over here, that is n is equal to 1 and going to infinity, right? Or we can also say that sigma a sub n, we can just write down in both manners. It would be impossible to find a finite sum of the series, right? If we just write down 1 plus 2 plus 3 plus 4 plus 5 plus up to n plus infinity, right? Because if we start adding the terms, we get the cumulative sums. What do we get? We'll get 1, 3, 6, 10, 15, 21, and after the nth term we get n into n plus 1 by 2, which becomes very large as n increases, right? So it would be impossible to find a finite sum of for the series, right? We have an example over here. This table shows that we add more and more terms, and these partial sums closer and closer to 1. So you can see over here, I'll just explain you the concept of the partial sums, but you can, first of all, you have to see over here, that is, when we start from our first term, this is the first term, second term, third term, first, second, third, right? And our values are sum of this n term is actually not so accurate or so close to 1, but as we move towards our 25th term, right, and is equal to 25th, then we see that it is getting closer to 1, right? So that is an example how we just get closer to a particular value. Okay, now I should explain this partial sum to you as well, right? What is this partial sum? Partial sum is a sum of a part of the sequence, right? Remember, a part of sequence, not the whole sequence, just a part of sequence. It is also known as finite series. It is unlike the sum of infinite terms, which is infinite series, right? So you see, in fact, by adding sufficiently many terms of the series, we can make the partial sums, right? It seems reasonable to say that the sum of this infinite series is 1, and to write, we can write it down in this manner, right? So we have this half, then fourth, then eighth, 16th, and then up to 1 by 2 and 1 by 2 power n plus up to infinity, right? And it would be equal to 1, right? Okay, so here's the concept of partial sums, right? So when we say that s sub 1 is equal to, it would be a1. When we say s sub 2, that would be having 2 degrees involved over here. So we will sum the two terms over here, a1 plus a2, right? And when we have s3, we will sum 3 values of that particular series, right? Or that particular sequence. And then when we have s4, we will be summing those 4 values from the sequence. And in general, we have s sub n, which is equal to a1 plus a2 plus a3 up to an, right? We will not be moving ahead from an, because an is our nth value, and that is what we required over here. So it would be denoted as sigma ai, where I is equal to 1 and it goes to n, right? So these partial sums from a sequence s sub n, which may or may not have a limit. Okay, now we just moving to the limit part of this series. So if our limit exists, right? If our limit of s sub n, where n approaches towards infinity, exists, then is preceding example, we call it sum of the infinite series. All right, so we have over here, you can see that when we have this sigma a sub n, and n is equal to 1 over here, and it goes to infinity, right? So let's s sub n denote its nth partial sum. So we can just say that this is the nth partial sum, right? Suppose this s sub n is s sub 18, right? And we can say that it is going up to a of 18th, right? So that would be the 18th term. Understand? If the sequence Sn is convergent, and limit n is going towards infinity, where Sn is equal to S, which is sum, exists as a real number, then the series sigma a sub n is called convergent, and we will write it as a1 plus a2 plus a3 up to an up to infinity is equal to S, right? And this would be the notation of this particular equation, right? But the number S is called sum of the series over here. This number S would be called the sum of the series. If the sequence Sn is divergent, if it is not convergent, if it is divergent, then the series would be called divergent over here, right? Thus, the sum of a series is limit of the sequence of partial sums. Right. So when we write this sigma an, where n is equal to 1 and goes to infinity, is equal to S, right? We mean that by adding sufficiently many terms of the series, we can get as close as we like to the number S. So it means that similarly, we were getting closer to 1, we can get close to our S if this limit exists, right? And if it goes to the infinity, if our n goes to the infinity, right? So notice that sigma a sub n, where n is equal to 1 and goes to infinity, would be equal to the limit sigma ai, where n goes to the infinity and I is equal to 1, and it will be going towards n, right? Okay, so here we have an example. So an important example of an infinite series is geometric series. So when we take the geometric series example, what do we find? That we have an equation in this form: a plus ar plus ar square plus ar cube up to ar raised to power n minus 1 plus up to infinity, right? And then we will write it down in the form of sigma ar power n minus 1, where n is equal to 1 and goes to infinity. And remember, our a should not be equal to 0. It must be unequal to 0, right? So each term is obtained from preceding one by multiplying it by the common ratio r. So each term over here is obtained from the preceding one, the previous one, right? Multiplying it by the common ratio r, right? But if we have our r is equal to 1, if we just have this r is equal to 1, then these powers gonna be useless, and we will have a plus a plus a plus a plus a plus, right, up to a, and this would be an a and approaching towards negative or positive infinity, right? Since limit s sub n doesn't exist, right, limit where n is approaching to the infinity, right, it does not exist, the geometric series diverges in this case. All right, so when we have our r is unequal to 1, right, so what do? We have this value where s sub n is equal to a plus ar square, right, and same ar power n minus 1, and our r into s sub n is equal to ar plus ar square plus ar power n minus 1 plus ar power n, right? So what do we find over here? We will just subtract these equations, right, and we will get our s sub n is equal to a into 1 minus r a into 1 minus r power n, right, by 1 minus r. So this would be our definition number 3, right, our equation number 3 that we will be finding with the help of subtraction of equations from this value. Okay, now if our r is greater than -1 and less than 1, we know that r power n goes to approaches to 0 as n approaches to infinity, right? So limit s sub n, where n approaches to infinity, is equal to limit a into 1 minus r power n by 1 minus r, where our n approaches to infinity, would be equal to a by 1 minus r minus a by 1 minus r, right? And limit r power n, where n approaches to infinity, would be a by 1 minus r. So it means that the geometric series is convergent and its sum is a by 1 minus r, right? We can clearly just see that. So the sequence r power n is divergent, so equation 3 will limit s sub n and n approaches to infinity does not exist. Therefore, the geometric series diverges in those cases. Alright guys, I'm so sorry for my phone's malware, because I don't know what's going on with that. I'm going to do the next slide and it is not helping me at all with that. Okay, so we summarize the results of example 2 over here. The geometric series where sigma ar power n minus 1, where n is equal to 1 and goes to infinity, is equal to a plus ar square plus up to infinity, is convergent, right? If r is less than 1 and its sum is something like this, right? And if r is equal to or greater than 1, the geometric series is divergent. It means that it is going towards infinity, right? It is not restricting itself toward a particular value. Okay, now we have another example, that is harmonic series. So it says that show that the harmonic series where sigma 1 over n, where n is equal to 1 and goes to infinity, right, is equal to 1 plus half plus 1/3 plus 1/4 plus up to infinity, is divergent. So when we see this example, so for this particular series, it's convenient to consider the partial sums. We have to deal with the partial sums, right? And then we will just add those partial sums to show that how large they can become, right? So here we have S2, right? Our S1 was 1 and our S2 was 1 over 2. So when we take the partial sum of S2, it would be 1 plus half. When we take S4 over here, it would be 1 plus half 1 plus half plus 1/3 plus 1/4. That is these are the 4 values actually, and these are greater than our 1 plus half plus 1/4 plus 1/4, right? Because this particular value is greater than this value, right? So what do? We will write it down by 1 plus half and then another half. 1 by 4 plus 1 by 4 is gonna be equal to 2 by 2. So it would be half plus half, 2 by 2, right? So 1 plus 2 by 2. This is gonna be our S4. Now we are dealing with the S8 over here, right? S8 would be 1 plus 1 by 2, that is our half, right? Plus 1 by 3, 1 by 4, plus 1 by 5, 1 by 6, 1 by 7, plus 1 by 8. So it is greater than 1 plus over here. You can see over here. Now this value is greater than this value because we can see over here we have 1 4 plus 1 4, where over here we have 1 3 plus 1 4, and 1 over 3 is bigger than 1 over 4, right? And here we have 1 by 8 plus 1 by 8, 1 plus 1 by 8. On the other hand, we have 1 by 5 plus 1 by 6 plus 1 by 7, then 1 by 8, right? So it means that we will be getting half from this equation, right? And this is more than half. This is the bigger than half, right? So what do? We will get 1 plus 3 by 2. In the previous S4 we had 1 plus 2 by 2, but after getting another half from sorry guys, yeah, so after getting another half from here, it will become 1 plus 3 by 2, right? Now we are going to deal with S16, and S16 would be same way. In S16 we will have 1 by 9 plus 1 by 10 plus 1 by 11 plus 1 by 12 plus 1 by 13 plus 1 by 14 plus 1 by 15 plus 1 by 16, right? And it would be greater than our 1 by 16 plus 1 by 16, 1 by 16. So it is 8 times 1 by 16, right, over here. So this value is definitely bigger than this value. It's greater than this value, right? And we will be getting half. We're getting half from our this value from here. And what do? We will add that half over here, and it would be equal to 1 plus 4 by 2. Before that you could see it was 1 plus 3 by 2, but after adding the half over here as well, it will make it 1 plus 4 by 2, right? Similarly for S32, it would be greater than 1 plus 5 by 2. S64 would be greater than 1 plus 6 by 2, and in general it would be it would be S sub 2 power n, that would be greater than 1 plus n by 2. This shows that S sub 2 power n goes towards infinity as n goes towards infinity. So our S sub n is divergent. It means that it is going towards infinity, right? Therefore the harmonic series diverges over here. All right, now we have some characters of a series, right? So in theorem 6 it says that if the series sigma a sub n, where n is equal to 1 and goes to infinity, is convergent, then limit a sub n, where n approaches to infinity, is equal to 0. The converse of theorem 6 is not true in general, all right? Because if limit a sub n is equal to 0 and n approaches to infinity, we cannot conclude that sigma a sub n is convergent, right? So when we see the equation 7, the test of divergence, right? This is really important because we have to see whether it's divergent or not, right? In order to find out whether we are having this divergence over here or not. So if limit a sub n where n approaches to infinity does not exist, or if limit a sub n does not equal to 0, then the series sigma a sub n is equal to 1 and goes to infinity is divergent, right? So the test of divergence follows from the theorem 6, because if the series is not divergent, then it's convergent, because they are just two conditions, right? Either it's convergent or divergent, right? So limit a sub n is equal to 0 when n approaches to 0. Then we have theorem 8, which says that if we have sigma an and sigma bn are convergent series, then so are the series sigma can a sub n, where c is a constant, right? And sigma an plus bn and sigma an minus bn, right? So we have three equations over here. We can see that in the first equation we have our constant over here, and we can take this constant out right here before sigma, and we can just write down the whole equation as it is. And in the second equation we can see that we are having an addition over here. We have sigma over here, then an plus bn. So what do? We can write sigma an where n is equal to 1 and goes to infinity, plus sigma bn where n is equal to 1 goes to infinity, right? And in equation 3 it's the same thing, but we are having the subtraction over here, and we can see that sigma an minus bn where n is equal to 0 and goes to infinity. So it would be equal to sigma an where n is equal to 1 and goes to infinity minus sigma bn where n is equal to 1 and goes to infinity. So these are actually the characters of how, or we can say the properties of series, right? So guys, that was all about the series and sequences. So the basic theme is you have to see what is series and what is sequence, right? You have to mind the differences between sequences and series, right? And additionally, you have to know that how you gonna annotate that, understand? And last of all, you have to know that how you're gonna plug in the values over there of n. So if you have any kind of problem or question, you can just ask me in question and answer sessions. All right.